illustrating lectures that I prepared in the sense that there's either too much to say or too little. So it's going to be a little bit too much generalities. But the focus is going to be electroweak physics and the transition to beyond the standard model. Okay, and the two things I picked out to think about are ones that illustrate why electroweak is good for looking beyond the standard model. And basically what you're doing is you're fighting against effective field theory. You know, effective field theory, we've argued how wonderful it is. But if you're looking for new physics, it gives you the main problem. The effective field theory says that new physics comes in at order e squared over lambda squared, where lambda is the scale of new physics. And so if you're doing QCD at 1 GeV, that's a factor of 10 to the minus 6. It's a factor of 100 if you're doing physics at the electroweak scale, even if lambda comes in even as slow as 1 TeV. So your only choices are here. The tricks to get around this are go to rare stuff and to go to precision stuff. You need to beat against effective field theory to do that. And in both these cases, electroweak is good. And so what I'd like to do is take a look at some of the rare stuff, basically flavor physics, and a little bit of the precision stuff, which is some of the electroweak physics. And surprisingly, we've done actually an excellent job at doing this. For the past years, as we've been waiting for the LHC to turn on, we've done a great job of testing these things, and new physics could have shown up and it hasn't. And so there's a little bit of a worry associated with this, that we could have seen new physics and haven't. So I'll talk a bit about that too. Okay, so that's what I want to do. So rare weak decays. So let me take the following example. Let's take B goes to S gamma. Okay. The picture that we would draw for that is dominantly this guy. So B emit a photon, there's a W there, goes to S. There's also the picture like that, B gamma WW S. So depends a little on the mass of the intermediate states. The first one actually tends to be more important. The first one is the one I'll use to illustrate it. And so, of the general things that you think about when doing this, the first thing I'd like to just talk about is the operators that are involved. So basically, we'll do the operator product expansion. And so the first thing that you might try is something that looks like it starts with a B, ends up with a S, and has a photon. There's an operator that makes this transition. If you remember some things I've said earlier, this one is actually is not appropriate. It gets removed. It's part of S bar D slash B. The only way you can make that gauge invariant is to make that combination. And this guy you can get rid of by diagonalizing. And so that guy makes no contribution at all. And so you don't even bother calculating it. Okay? You, okay, you comfortable with that? That's the first thing we do. The operator that contributes, I mean, it's called O7 in some counting scheme, is S bar sigma mu nu B F mu nu. So that involves a photon in the field also. Okay. That's that is the operator that counts. So it is basically, when you're doing this calculation, you're calculating the coefficient of that operator. There's a potential problem. This is the sense that, remember, the weak interactions involve the left-handed quarks, and S bar left sigma mu nu B left is equal to 0. Okay, it involves, sigma involves two gamma matrices. You bring the left through two gamma matrices, you get 0. It's just like 0, no gamma matrices there. So this operator is either S bar right sigma mu nu B left, or S bar left sigma mu nu B right F mu nu. Okay. Well, that's okay. I mean, you can get those. It's not really a problem. The way you get this is when you have P slash acting on, let's take B left. So the current actually does have to involve B left. That's P slash 1 plus gamma 5. B, you bring this guy through there, it makes a minus sign, equals 1/2 1 minus gamma 5 times M B B, so it's a M B B right. Okay, so you can get these fields by this so-called mass insertion. But that actually tells us the structure of the operator. The operator, there's O7 is MB S bar left sigma mu nu B right plus MS S bar right sigma mu nu B left. Okay. So actually, there could be a relative phase between those two. I'm pretty sure it turns out to be a plus sign. But in any case, you drop that guy since MS is so small compared to MB. But this already tells you that this has an extra suppression. The other dimensional factors that come in are going to be the W mass, the top mass, things like that. This, well, we think of MB as a big mass. It's actually small on the electroweak scale. So this operator ends up being more suppressed than you might otherwise think. Okay? But look, just to contrast this, let's look at B goes to S, lepton plus lepton minus, mu plus mu minus, typical case, or electron. Okay, is it the same story? I draw the diagram. Here's the diagram. let's call mu plus mu minus, okay? B goes to S. Okay, since I wrote contrast, you can guess the answer is no. Here the operator is the following. If this is a gamma there, it's the electroweak penguin operator. It's S bar gamma mu 1 plus gamma 5 B mu plus mu bar gamma mu mu. Okay, this current down here is a vectorial, so there's no 1 plus gamma 5 or 1 minus gamma 5 involved. So this guy lives through that vertex there. Now this seems a bit funny. How can you can't get this for the real photon emission? Why can't you get that type of operator, but you can get it here? Okay, the answer goes through the following: is that the way it gets generated is the upper vertex there is really like the following. It's like S bar left gamma mu B left, and then Q mu Q nu minus G mu nu Q squared A nu. So this is the upper vertex. So if you do the calculation, you get something that's equivalent to that. It's basically has those of course could be derivatives, but you're doing the calculation in momentum space. And so this is like a charge radius. Charge radius is something that goes like Q squared times the bare vertex. And then when you put this in with a propagator, the propagator goes like 1 over Q squared. So this ends up going like Q squared over Q squared times S bar gamma mu 1 plus gamma 5 B, and then mu bar gamma mu U with no propagator effect at all. That cancels out, and it's just a constant. Okay, so it's an interesting, maybe. It's actually a little more complicated than that. But maybe I won't go into that right now. We'll reserve that for some other moment. Okay, but so this guy has no MB suppression, but it does have an extra factor of the electric charge sits there, which when you get the decay rates is another power of alpha, so there is still some suppression there also. So these both turn out to be rare decays. Okay? Questions about that part? So this is the helicity chirality structures. When you start off one of these rare processes, you always go through this little analysis. What's the operator? What's the form of the answer going to be before you start the calculation? If not, then let's look at the more detail. So flavor changing neutral processes. Okay, so this is a typical example of what flavor changing neutral currents is what one often calls it. So it's a gamma B goes to S. It's not a charge current. It is not a charge changing process. And there are some other features that I want to do about this. The first thing, how worth it is it to me to write out the amplitude? I'll just write out the key. This matrix element. If you write out the propagators, it has an integral d4k, 1 over k slash minus some mass from that propagator, 1 over k slash minus the mass from the other propagator, 1 over k squared minus mw squared from the last propagator. So it's divergent. Okay. And it truly is divergent from this. So at least it looks superficially divergent. But there's nothing to absorb the divergence into. You know, if you try imagining how am I going to get rid of that divergence, there's no coupling constants associated with that. Okay. So we look like we're in trouble. But the day is saved by the CKM Unitarity. Okay. Otherwise referred to as the Glasgow-Iliopoulos-Miani mechanism. Okay. And it comes from looking at what's actually here. The intermediate state there can be, so B connects up to top quarks get up to strange quarks, B connects up to charm, and it connects up to up. Okay, and so the matrix element is also proportional to VIB, where I is going to be UCT, and VIS star times the integral that depends on the mass of the eye. Okay? The way it saves the divergence is that the divergent piece is independent of the masses. And then sum over I, VI, S star, VIB is 0 by CKM unitarity. Okay. So the divergence cancels, and we're left with something finite. But we can do better than this. So that's one big lesson. And the second thing is that we can get the form of the answer out. Okay. By looking at a little bit more detail, we have V star T TS V T B, this integral of MT, V star C S V B C, I is a function of MC, V U S V B U. Okay. If you go back to the CKM parameterization, VUS is a parameter that's of order lambda. VUB we called A lambda cubed rho plus I eta. You go V CB was A lambda squared. VCS is 1. I mean, yes is 1. That's the diagonal piece. VTB is 1. VTS is A lambda squared. One of these actually comes with a minus sign. I forget which. It's this guy right here, in fact. Because they have to, if you just plug through, they all add up to 0. So that this term is suppressed, and we end up with VCS star VCB I of MC, or MT, let's make it MT, minus I of MC. And so it's the cancellation of two types of terms in these integrals times some overall suppression, which is it's actually non-trivial suppression already from the CKM elements. They all have these forms. So all flavor-changing neutral processes involve differences. These cancellations are universal, and there's two types. Typically, if the masses were small, you get two types. Either they get the form delta I is m t squared minus mb squared over mw squared. So there's power suppression, or delta I is log mt squared over mb, so that should have been c, of course, over mc squared. Okay, now for the tau quark being pretty big, these forms aren't exactly true anymore. It's more complicated than this, but there's two general things to say here. One is that all these functions are calculated you don't really have to do these things. They're calculated by Enami and lim. So if you see Enami lim functions, it's just these process functions. So anything that looks like this plus this, that, or box diagrams that look like this. So those are the typical ones that you get in rare flavor-changing decays. You write out the integrals and you look up the Enami lim functions. The other feature that's crucial is top dominance. Okay. MT is almost always the crucial intermediate state. Okay, and it comes from these type of diagrams, these type of cancellations. but anytime the top can contribute, it almost always wins out. There's the one exception. There is one exception. Um, the mass difference of neutral kaons, so K0 and K0 bar split into K long and K short. The mass difference between K long and K short is the top quark is unimportant, and it's just from the particular CKM factors that arrive there. Okay. So those are the general features in the standard model. So flavor, rare, and beyond the standard model. Okay, let's just talk briefly about this. The basically your goal, if you're trying to find physics beyond the standard model, is to find something where the standard model is relatively suppressed so that other things can come in. So something like this is good. The issue here is loops are sensitive to all physics. Though again, you're fighting against effective field theory. So let's, if we take an example like our B goes to S gamma case, B goes to S gamma, we could imagine adding in something that goes like, again, the same picture, but this could be, for example, a supersymmetric W, and this could be a squark, okay, T-twiddle or something like that. The basic point is that anything could enter there. And some types of theories actually end up with big contributions. So the power counting here ends up going like this one is MB has a 1 over MW squared from the propagator times V CS star V TB times this function of MT minus MC. So there's all our factors there. And if you take another theory, depending on how the analysis goes, this could be MT twiddle over MW twiddle squared. There could be different angles, so let's call it 1 just to be favorable, and times something maybe that there is no Jim suppression. Supersymmetry actually would have some equivalent Jim suppression, but let's imagine that. Well, you can get, clearly you're fighting it as always, you're fighting against the 1 over the new scale. So this suppression here, if this could be 10 times bigger than the W or more, so there's a factor of 100 there. But if you were able to pick up a thing in the numerator, this mass here can easily be 100 times that mass also, so it could, in principle, come in at the same order. Plus, you could avoid 2 orders of magnitude of Jim suppression or so. So you can be quite sensitive to that. And another example, probably one of the rarest examples, would be K long goes to pi naught nu bar. Okay. K long is a long-lived kaon, so it's actually good for looking in its rare decays. This particular process occurs for the new, through S goes to D. You have to come out with a Z0 here to get to a nu bar. So that's relatively suppressed. If I just wrote a new physics, so Hamiltonian for new physics is 1 over lambda squared, so there's my scale, times the operator, S bar gamma mu 1 plus gamma 5, D nu bar gamma mu 1 plus gamma 5 nu, just to parameterize new physics. So 1 over lambda squared parameterizes new physics, and I write gamma new physics over gamma the standard model. Okay, it goes like 1 over lambda squared divided by the factors of the standard model. I don't know. I have some written down here, but let's not do it. But the interesting thing, the point of doing this is that if I take lambda to be 1 TeV, so let's make this ratio is 10 to the 8. Okay. So you've really beaten the odds here. The standard model is suppressed enough that if there was new physics at 1 TeV, your new physics is 8 orders of magnitude bigger than the standard model. That's already ruled out. Okay. If you say this is of order 1, is lambda is 10 to the 5 GeV. So it's not, it's a 10, so 100 TeV gets us down to that. Did I get that? Yes, that's because that's 100 TeV because it's 10 to the 8th. It goes like lambda to the 4th. Okay, so this type of process has already probed new physics at scales like that. We can go through all the phenomenology of lots of different things. I can't. Or in principle, we could. At one stage, I got a good deal of press for saying at one conference about these decays that this will allow us to find the smoking gun of new physics before we find the dead bodies at the LHC. And that was really the motivation for a lot of physics for a long time. Was this figuring that you, by looking at these rare processes, you have a good handle on new physics. And we don't find it. So as I say, it's bothersome. What you will see now discussed is a paradigm that's come to try to explain that. So minimal flavor violation. The problem is that we have many opportunities. We should have seen physics. Well, what's wrong with these estimates that I did here? If I go back and critique this little estimate that I did right here, You see, one of the problems is I just assumed a constant 1 over lambda squared, whereas the standard model had all these CKM and GIM cancellations going on. And so if I put all the same CKM and GIM cancellations in the new physics, then the new physics would be small compared to the standard model, just because the scale would be bigger, but all the cancellations would be going on. So the solution to the problem is to build in GIM type cancellations into your new physics. So minimal flavor violation is basically the statement that says that flavor violation comes with a universal thing, which is basically the CKM matrix. The factors that govern flavor violation in other areas also carry the same factors. Now that's a pretty big hypothesis. It would imply then that if I was doing this H new physics, I should have really written VT S VTD over lambda squared times the operator. Okay, because that's the CKM factors that get built in to the standard model, and then of course all the constraints go. And if you do this, there's essentially no constraints. Okay, so I expect you'll hear more about this as things develop, because it's the paradigm for how you get rid of flavor violation constraints on new physics. But it's a bit ad hoc, so it's all there's no great theoretical motivation. Okay. Questions on those guys? I was going to move on now to precision stuff. No? Okay. So, the precision test. Actually, we're pretty well set up for this, given the calculation we're doing, and you can understand how it comes about. The basic physics in a lot of these tests comes from the vacuum polarization. Okay, and so let's imagine we're doing this, some process like this. So these are W's here, or Z's. Okay, so when I do scattering, low energy scattering, I do W exchange and I do vacuum polarization on top of it, etc. This goes into G Fermi. This goes like G2 squared over 8, 1 over Q squared minus some MW0 squared minus the vacuum polarization function as a function of Q squared. Okay. When Q squared goes to 0, this turns into G Fermi. It's actually minus G Fermi over square root of 2. So the G Fermi involves the vacuum polarization at Q squared equals to 0. But that's not actually MW, but MW squared is MW0 squared plus pi of MW squared. Right? So just like in the calculation that we're doing for the sigma model, the sigma mass is defined on its mass shell. However, when we're doing the low energy effective theory, the low energy effective theory involves the exchange at Q squared equals to 0, and so it doesn't contain some of the loops in that process. Well, the same thing happens in this standard model. These then lead to tests because you can probe the difference between these two functions, and it turns out to be pretty strong tests. So at tree level, we have mw squared equals mz squared cosine squared theta, the Weinberg angle. And you can do two things. You can measure this at low energies, where you compare g2 squared over mw squared to the same g2 squared over mz squared cosine squared theta w, which enters the neutral current processes, so Z exchange. Or you can do it at high energies on the poles. So you find the poles in those amplitudes. And these things are no longer exact relations because they have shifts. One or the other could be chosen to be an exact relation to define cosine theta w, but then the other one has a change. And so it turns out that much of the physics is in these vacuum polarization functions. So if you take these pi mu nus, let's put the mu nu downstairs. That's a function of q squared. And we Taylor expand it. So I'm going to use the notation from our book. Q squared a prime I plus dot 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 g mu nu. That turns out to be the piece that's relevant. The q nu pieces drop out of everything. Okay, so these are a set of vacuum polarization functions, and you can actually have 4 cases. You're going to have W, so W loops. You can have ZZ. You can have photons. And the 4th case is a Z mixing with a photon. So you can have something where a photon comes in here. You have a vacuum polarization. A Z comes out there. Now, if you choose your diagonalization right, that should vanish on the Z pole, but it doesn't vanish at all q squared. Okay, so there's our players in this game. We have basically 3 parameters that are important for us here. They can be taken in the original theory. It's the G1 for U1, G2, and the Higgs vacuum expectation value. Okay, if we're doing precision, we want to convert those to three numbers that we know precisely. So we know alpha, G mu, mz precisely. So rather than express everything in terms of them, we are interested in expressing them in terms of those quantities. Now, we're not going to get into so much detail that's that important, but for this, of these parameters that you have here, we have some that are not that go into these precisionally known parameters. So there's a set of renormalization constants. Okay. We know one of these already. We know that if you have the photon amplitude, the vacuum polarization function at q squared is equal to 0 goes into renormalization of alpha. So delta alpha over alpha is minus, I have copied down the photon vacuum polarization function. Some of it goes into the W math, so delta GF over GF is WW, the vacuum polarization function for the, some of it goes into the Z, so delta mz squared over mz squared is, I'm just copying out of the book, is a 3 over mz squared minus a prime 3 3 refers to the third component of isospin. Okay. I guess I forgot to say that there's also current conservation constraints that says that pi gamma gamma of 0 is 0 and pi gamma 3 of 0 is also 0. Okay, this comes, again, those are things that you saw the first one. You know, the vacuum polarization function starts off as q squared g mu nu minus q mu q nu. That's the usual one from that. And then the other one involving the photon also. Okay, so we start out with 6 of the, let's see, we have 8 of them. Let's see if I got my counting right. 8, there's 4 cases, 2 functions, there's 3 renormalizations and 2 missing. So we're left over with 3 parameters. So there's three combos. Okay. These last 3 combos are parameterized by capital S, capital T, and capital U. The remaining pieces. And I'll just write them out. 4 sine squared theta W over alpha, A prime 3 gamma over sine theta W minus A prime 3. So various combinations. There's T 1 over alpha A33 minus AWW 1 over alpha m over 1 over mw squared. And, well, for completeness, 4 sine theta w over alpha A prime 3 minus A prime WW. U turns out to be the least important. So the these parameters have been used to analyze the precision data. I'll show you some in a minute. Okay. So, and they're traditionally used. There are standard model contributions which you subtract off. Okay. Do I have a good? I don't have a good example of that. I know the following. There's the two main standard model contributions are there are mt squared dependencies, and there's dependencies on log of the Higgs mass. Okay, there's no straight dependence linearly on the Higgs mass. It's only on logs. That turns out to be a crucial factor because it tells us that all of our tests are only sensitive to the log of the Higgs mass rather than the Higgs mass itself. So when you change it by a relatively wide range, you get relatively small changes. Okay. The other thing however, the thing that's most important is that S, T, and U are sensitive to new physics. Okay, and that, again, comes from loops being sensitive to things that sum over all energies if you sum over stuff there. And my favorite example, which I still find a little puzzling, let's take a fourth generation. Okay. The fourth generation, and I'm just going to add quarks here. Well, I'm adding either, but here's S looks like the following. So you do the calculation. S is 1 over 2 pi times 1 minus the hypercharge of the doublet times log m of the up type squared over log of the down type squared. Okay, and T, well, there's some factors. Yeah, I'll write it. Some factors, and then this has things that are not in logs, mu squared plus md squared over 2 mz squared minus mu squared md squared and mu squared minus md squared mz squared log mu squared over md squared. And U it turns out to be unimportant. So there's a couple things I think are funny about this. The S does not decouple. Let's discuss that for a moment. This only depends on the ratio of the up-type quark to the down-type quark. It doesn't depend on the overall magnitude. So if they existed at the Planck scale, you'd still get a contribution to S. Okay? Seems really odd. So this, yeah, it's something of order it looks like 1 over 2 pi when the dust settles, unless if you take them degenerate. But it's sensitive to any mass all the way to infinity. And this seems to violate Appelquist-Carrezone. Appelquist. Okay, and it does really. You know, Appelquist-Carrezone says that as the masses get heavy, that their effects get suppressed by powers of 1 over the mass or go into renormalization constants. This isn't the renormalization constant. This is a free parameter that's in addition to that. But and so it's an instructive case. But the way it's often explained is that the masses are Yukawa couplings times the Higgs Vev. The Higgs Vev is already fixed. So to take the masses large, you have to take gamma goes to infinity. So mass going to infinity is gamma going to infinity. And so something goes wrong with Appelquist-Carrezone because as you take your mass heavy, it's trying to decouple, but your numerator, the thing that gives you the mass, is going to infinity. So normally we would have thrown this out, but you can't. That's a problem. But it's true. The other thing is that he is let me call it SU2 breaking. Okay. The limit that I took of the masses being equal, it's actually hard to look when you look at that formula to see it. But it's one of these things that there's a 0 that comes from the log divided by the 0 that comes from that, if I set the masses equal to 0. And when those, do I have a missing a factor of 2? Anyhow, I'm trying to do the, no, it works. I'm sorry. When those are equal, then these two masses are equals cancels that 2. So these two things cancel, and you have to do the Taylor expansion to higher orders. This goes to 0 as mu goes to md. Okay, so that's a measurement of, in some sense, when you have new physics up there, how much it breaks the SU2. That's a little more general than this particular calculation. The data say roughly that S is less than about 0.2, T is less than about 0.1. There are correlations, but this tells you that if you had just one strange quark, you're already starting to get into trouble with both of these. And if you had a quark doublet and a lepton doublet, you are in trouble already. So another whole generation is in trouble. And so you can see that it's actually relatively sensitive to new physics. The type of tests that lead to these constraints are, one, you can just do precision fits. At the z-pole. So this is the summary of physics from LEP. And two, the other thing you can do is high energy versus low energy comparisons. Okay. So, let me just give you one example here, which is the example that I set up there. If I look at rho is mw squared over cosine squared theta w mz squared, that's 1 plus delta rho. Okay. You can, if you define these by their z-pole values, and then, so that's where the definition comes from, and then you can measure them at low energies also. You can do a comparison of the same parameters at high and low energies. And this guy turns out that delta rho is alpha times the t parameter, and that the s parameter is also related to it as 4 s squared, those are the Weinberg angles, over alpha delta rho plus another combination something that we call delta kappa, which is the shift in the Weinberg angle. So those then lead to the constraints on this. And so these precision tests are then the next set of constraints. So again, there's little room for new physics in these tests. It's a little frustrating. Okay. Anyone want to ask about that? Those guys? So let me just close with some expectations for physics beyond the Standard Model. Just sort of interesting just to run down what there is and why we might see it. So the first one, I think the most solid, is dark matter, or something. There's something going on there. Something is needed. The dominant constraint here, the dominant idea, is something at the TeV scale with weak couplings. So that works, but it actually has to be less than weak interaction couplings. I put a little less than, because if you, I always was carrying in my mind that you could have weak interaction stuff there, but if you go and look at it in detail, the couplings are already constrained to be smaller than weak interaction couplings. So if you just plug in the standard weak interactions, you're not going to get something. There's the second constraint is inflation, or something. The third we need is baryogenesis. The fourth argument is always the scale of electroweak symmetry breaking. Okay. Let's just pause here for a moment for this. this guy. It's the argument goes as follows. You know, we know we can renormalize the standard model. However, for once, let's not use dimensional regularization, and let's use a cutoff. If you use a cutoff, you find out that the Higgs mass picks up contributions that are different from the usual contributions because they go quadratic. So here's the diagrams that are involved. There's that type of diagram with, so here, this is actually a Higgs now, so it should actually be a solid line, I guess. Higgs, and this could be some fermion, anti-fermion, or you can have a Higgs. Here's lambda phi to the fourth. Higgs, Higgs, Higgs. So scalars. Those are the two types of graphs. And the shift in the mass of the Higgs, it's gamma for that fermion squared over 8 pi squared lambda squared plus something plus log lambda. And it's lambda over 16 pi squared lambda squared. Again, I'm not doing the coefficients. I got the right coefficients out in front. It's actually a minus sitting there. So these two contributions are the ones that are quadratically divergent. They come with opposite signs. If you're just doing renormalization, it's okay. You can renormalize them. But there's something annoying about them in that if you take these scales much bigger than the standard model, then you have to really, 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 really fine-tune your parameters. Okay. Now, with logs, you can take lambda to be the mass of the universe, and this shift is of order 1. So it's a small infinity. It's my famous small infinities. Where you take this to be the mass of the universe, you're in big trouble, because then you have to fine-tune it by 10 to the 80 orders of magnitude. So this is the argument that says that there's fine-tuning involved. To get MH. Okay. This argument leads to the expectation, so maybe put a question mark there, but that's certainly what the field does, that there's new physics at lambda that makes these things finite. Makes the lambda squared disappear. Okay. So for example, if you chose for every fermion there was a scalar in the theory, and you chose gamma, f, and lambda to be related in just the right way, those would cancel, and you'd have only the log lambdas left over. The lambdas don't cancel. Okay. So that's the argument. Supersymmetry has this. There's for every fermion diagram, there's a scalar diagram. The coefficients just work out so that they cancel. You can see whether you think that that's a compelling argument or not, but that's what it is. And 5, let's just do dreams of unification. The approximate running of the coupling constants almost matches. There. Prima, is that a good enough drawing there? They almost cross. These are the running coupling constants, q squared as a function of q squared. Yes, one would always like to take these theories and make it more fundamental theory. So of these arguments here, let's just go over them just briefly. The two that are really relevant for our lives in the near future are the dark matter and the fine-tuning issues. Both those are motivations for physics at the TeV scale. Inflation and baryogenesis can be something else. And you can solve the unification by having other stuff somewhere between here and high energies. So it's not compelling that we have it at low energies. Anyway, I guess I will stop there. That's about what I wanted to get through anyhow. You know, I wish I could have done more on the phenomenology, more details, but that's the basic sets of using electroweak to get beyond the standard model. So next 2 lectures will be supersymmetry, then 2 gravities. Then we're done. Okay?